Hello everyone. Electromagnetic Induction Part 1. Faraday's Law of Induction and Lenz's Law. In this video, I will be discussing the Faraday's Law of Induction as well as the Lenz's Law. So first we shall see the introduction to electromagnetic induction. Oersted, Ampere and a few others conducted experiments to prove that electricity and magnetism were interrelated. These scientists found out that moving electric charges produced magnetic fields. This led to the question as to whether it was possible to produce electric current from magnetic fields. And experiments were conducted by Michael Faraday in England and Joseph Henry in US. These were conducted around 1830 and were helpful in proving that electric currents were induced in closed coils subjected to changing magnetic fields. And the phenomenon in which electric current is generated by varying magnetic fields is called electromagnetic induction. Now we shall see about the experiments of Faraday and Henry. This figure shows a galvanometer connected to a coil, and if we move a magnet such that the north pole of the magnet is near to the coil, we can see that a deflection occurs in the galvanometer. The deflection occurs in the galvanometer as long as there is the motion of the magnet. If we move the magnet in the opposite direction, the galvanometer shows a deflection in the opposite direction. This shows that a current is induced in the opposite direction. From this experiment, Faraday concluded that the relative motion between the magnet and the coil that is responsible for generation or induction of the electric current in the coil. He also found out that the intensity of the current varied with the speed at which the magnet was moved inside the coil. Did another experiment in which the magnet was replaced by a coil C2 connected to a DC source as shown in the figure. Then the third experiment done included two coils which were kept stationary. That is C1 and C2, the coils were kept stationary. But in this case, a key was used. When the key was pressed, it produced a current in the coil C2, and this change in flux induced a current in coil C1. It was seen that current was only induced when there was a change in the magnetic flux. That is only at the time when the key was closed or opened. Now we shall take a look at magnetic flux. That is, for that we can consider a plane of area A kept in a uniform magnetic field first. The angle between the magnetic field and area vectors is theta. In this case, the magnetic flux through the plane of area A is given by phi b is equal to dot product of b dot A, that is equal to BA cos theta. Now, if the surface is a curved surface and it is kept in a non-uniform magnetic field, then we can extend the formula for the plane in a uniform magnetic field in this case. That is, phi b is given by the sum of B1 dA1 where dA1 is a very small area of the curved surface and B1 is the magnetic field through that surface, which gives sigma all. That is, it is the summation of all such elements of area dAi having magnetic field Bi passing through them. The SI unit of magnetic flux is Weber or Tesla meter squared. Magnetic flux is a scalar quantity. Now we shall see about the Faraday's law of induction. The statement is the magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Mathematically, we can write the EMF E, which is induced, is equal to negative of d phi b by dt. It shows that the induced EMF is in a direction opposite. In the case of a closely wound coil of n turns, change of flux associated with each turn is the same. Therefore, the expression for the total induced EMF is given by epsilon is equal to minus n into d phi by dt. We know that phi b is equal to Ba cos theta. Hence, it is possible to induce a current in a coil by changing the magnetic flux, the area, as well as the angle theta between the magnetic field and area vectors. Now, we shall see about Lenz's law. Lenz's law explains why there is a negative sign in this equation for Faraday's law. Lenz's law is as a consequence of conservation of energy. In 1834, German physicist Heinrich Friedrich Lenz deduced a rule known as Lenz's law, which gives the polarity of the induced EMF in a clear and concise fashion. It states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. We can use Lenz's law to explain the direction of current in the case of the Faraday's experiment where the magnet was moved inside a coil. That is when the north pole was close to the coil and when the magnet was moved, a current was induced in the anti-clockwise direction which opposed the motion of the magnet inside the coil. And when the magnet was moved in the opposite direction, the current induced in the coil was also in the opposite direction, that is in the clockwise direction. This is a consequence of conservation of energy. Here, the energy spent in moving the magnet is dissipated as heat by the current moving through the coil. So this is the end of this video. In this video, I have explained the Faraday's law of induction and the Lenz's law. If you have got any doubt, please comment in the section below. Thank you.